Welcome, Sendil sir. Good evening, sir.
Madam, good evening.
Good evening, sir.
Yeah, good evening, ma'am. We can
Meher
start.
ma'am. Yes,
John.
sir, we can start, sir.
Sir,
Meher ma'am, you can start.
Yes. Um, with a new day comes new strength and new thoughts by Eleanor Roosevelt. A very good evening to one and all. We, the Department of Computer Science, once again welcome all the participants to this 2 weeks workshop on analytical tools for image processing organized by the department as part of MHRD RUSA 2.0 biomaterial. It is our day 8 of the workshop. Day before yesterday, we have started with the session on secure network analytics with deep learning and transfer learning by Dr. T. Sendil Kumar, Associate Professor, Computer Science and Engineering Department, Amrita School of Engineering. The session threw us a light on the basic terminologies of deep learning, network, convolution neural network, and different resources available to perform image processing techniques and phase deduction techniques. The session was found really informative and interesting and provided everything that is needed to kickstart a research on image processing. And today, let us continue the session with Dr. T. Sendil Kumar. Sir, now the session is yours.
Okay. Thank you, ma'am. Thank you to all the participants and organizers for facilitating the things. So today's session we would take through an implementation which is related to activity recognition, right? And we will also share you an implementation which you can also do it offline with Python for activity recognition. So many have come from the organizers on link. Please keep that link for your reference. And there is a step-by-step document also that is shared, which will guide you to complete the process. Voice is not clear. Am I clear now?
Yes, sir, you're clear.
Let me get things clear. Okay, am I clear now?
Yes, sir.
Okay, one participant has put, ma'am, actually voice is not clear.
Some disturbance is occurring, sir. Please.
Clear, sir? Hello? Pankaj Kumar Singh, sir. Am I clear now?
Yes, sir. It's okay, sir.
Okay, fine. So today's session we will walk through on concepts on how to take deep learning with optical flow for activity recognition. Okay, as I said, an activity which is suspicious can be understood as a situation where your security is a big question, right? So that is what we will discuss today, and we will also take through discussions on transfer learning and understand how transfer learning is connected to deep learning process. Okay, so I'll share the screen. See, when you actually move from images to video, right, or couple of images that are related to be part of a video, then we are having a challenge that we are not going to detect only pixels. We are going to detect moving pixels. When there are going to be moving pixels together, then there's a need for estimating the motion. So motion estimation has got a lot of challenges, especially in research problems. One major challenge with motion estimation is like it is sometimes very hard to find motion in certain places. For example, let's take you are going inside a forest and you visualize yourself, there are some trees, there are some leaves. You see some sort of small disturbance among the leaves. There is a motion, but with the motion, you are not able to conclude what is the object that is part of the motion. So moving pixels always provide a lot of challenges, and it is important to estimate the motion. When you are able to estimate the motions, then advantages you can actually find many interesting things from the given scene. One, you can actually be able to find what are all the objects, what are all the behavior of the objects, You can in fact track the objects, right? Tracking objects is very interesting. I'll also show you some videos on tracking objects at the end of the session also, right? And when you are actually looking at motion component, it is sometimes very hard to understand the motion because there are some sort of instabilities with respect to the motion because of some camera. There are some noise which you can call it as jitter. So this also gives you a next keyword called as video stabilization, right? Given a video and you are trying to propose a research problem to understand activities and conclude whether there is a security issue in the particular environment, you can also write algorithms for video stabilization also. Now, we will be taking through discussions with respect to understanding how this motion component can be handled. So material I am taking from Selsky book. This is a very standard book. In fact, people want to have a good walkthrough on feature extraction, feature processing, then motion estimation models. Please refer this textbook, Computer Vision by Selsky. There are other textbooks also which is being put in the slides here. Now, the first concept is something called as patch-based motion estimation. So when you come to patch-based motion estimation, the first category of technique is something called as feature. What is this feature-based method? Is we are interested in finding out the visual features in the given image. What can be the visual features? It can be corners. It can be some texture areas, right? For example, let's take, I'm asking somebody to look at an animal and say, is it a zebra? And then you will immediately get to your mind, yes, there's a texture for a zebra, there's a pattern for a zebra. I find a similar texture there, so naturally I'm concluding it is a zebra. Right? Okay. So you can extract some visual features which can be called as texture-based features also from the given video. Our next important thing would be is like when the motion component is going to be very large, when the number of moving pixels is very large, right, there you can actually assume feature-based methods to be a very important one. For example, let's look at the water, right, and you see an object floating. Based on the region of the object where it is floating, you can see a lot of motion. You put a small ball, right, there is a small movement of water. You put a big ball, there's a big movement of water around the object. So the moving pixels can together say that there is something which is an object and the size of the object characteristics are so and so. So this falls under something called as feature-based methods. The next one is something called as direct methods. What is this direct methods here is like you directly recover the image motion by concluding from the spatio-temporal part. So what is the spatio-temporal variations? For example, I take an image at one time, I take the same image at another time. I'm able to recover something with respect to the motion part, right? So I'm concluding that there is a moving pixel which I'm seeing at time t equal to t2. From there, I'm concluding that there is some sort of a feature that I'm able to extract. So the motion component can be done based on spatio-temporal image brightness variations also, right? And here, there are a lot of techniques that are being available, and it is generally said that it is more suitable for videos. Now, when you come to patch-based matching, right? So how do you look at your correspondences? So we generally go for a block matching approach, which is nothing but sum of square distances, which people know, right? So here you see an image which is on the left side, you see an image on the right side. You find a distance between them. So what you would actually say, you would say it is I suffix L minus I suffix R. But here we are actually going for a block matching approach. So you would say I suffix L of X dash plus D, comma Y dash, minus I suffix R of X dash, comma Y dash, the whole square, because it is some square distances, right? And you want to look at all the pixels in the image, so N will be of N of X, comma Y. So like this, you can actually compare the correspondences between the objects, between one image and the other image. So here we are talking about a patch-based process. Here, the first challenge you would come across is something called as brightness constancy equation. See, what is brightness constancy equation? Here we say that when we look at any pixel, we are assuming that the pixel is part of an image, right? X, comma Y. Now the same thing, if you say that there is a movement of the pixel, So how it is moving? It is moving across an x-axis, moving with respect to an y-axis also. So there's a displacement of pixel along the x-axis, and there's a displacement of the pixel along the y-axis also. So the displacement along the x-axis can be given as u of x comma y, and the displacement along the y-axis can be given in terms of v of x comma y, right? So you are trying to conclude saying that if I have images, I would like to conclude that I will try to assume that the brightness do not vary, right? So that is where you write a brightness constancy equation like this, right? So equivalently, we are trying to say that every time you take consecutive images, the brightness of the pixels is assumed to be varying very minimal. There you write as E of u comma v is equal to g of x comma y minus I of x plus u y plus v the whole square, right? U is nothing but your displacement along x, and v is nothing but your displacement along y. Now, when you linearize it using the Taylor series expression, you can write it as independent components with respect to x and y. So you would say it is I of x comma y plus I suffix x comma x of x comma y multiplied by u of x comma y plus I suffix y of x comma y multiplied by v of x comma y. Okay. You will see some mathematics, but it's really a very interesting concept, and you can apply it for variety of applications. Even the same concept I'm talking about, you can take it to medical images also, right? Now, what you see in your brightness constancy equation here is what is rewritten using the Taylor series expression like this, right? Only thing is here we are writing in terms of gradient with respect to x and y here. Now, when you take it forward and you try to generalize it as an optical flow constraint, right? What you would get is like this. Now, please look at this here. E of u comma v is given as I suffix x into u plus I suffix y into v plus I suffix t the whole square. So what we want to minimize is the rate of change with respect to u and rate of change with respect to v, right? This further we write it as I suffix x multiplied by I suffix x into u plus I suffix y into v plus I suffix t is equal to 0. This is with respect to rate of change with respect to x. Now when you write it in terms of y, what will happen here? I suffix y multiplied by inner component is I suffix x into u plus I suffix y into v plus I suffix t is equal to 0. So in general, what are we trying to conclude here is there is going to be some rate of change along x and y. Only then you can conclude there is a motion. So I suffix x comma I suffix y is not equal to 0, right? So hence you can rewrite it as saying I suffix x into u plus I suffix y into v, right? I suffix t approximates to 0. This is your optical flow constraint. Okay, this becomes your optical flow constraint. Now, when you take it to your algorithms, you will have two types of algorithms in the optical flow. One is called as your Lucas-Knapp, and next approach that you will have is something called as Horn and Schunck, right? Okay. So what is Lucas-Knapp will assume is, Lucas-Knapp will say, if I have a single velocity for all the pixels within the image patch, what is a single velocity? It is like there are certain pixels moving in the image. All the pixels in that region have the same velocity. Then in that case, you can write it the energy equation in terms of E of u comma v as like this, right? Here, what we want to minimize is we want to minimize the outer product as an independent component with respect to the gradient vector, right? Now, leaving the mathematics behind, right? Let's go and start understanding this patch analysis. Now, if you look at this here, this is one portion of the same image with respect to the motion being represented with respect to different lines. Now, here what you see is a motion displacement. You can see here, blue moved to here. Now you can see there's a motion displacement. Now the question here is, I'm interested in seeing all this motion component. Now, if you want to do this, then in that case, you should understand that there is a motion with respect to this region, which is got displaced to this region. And from here, it's having motion around everywhere, right? It's like you have a ball, you toss the ball, right? The ball pitches to a particular direction, and from there, it pitches in all the directions, right? So here, how do we solve this? So here, what is suggested is we come across with the second type of problem in optical flow, which is called as an aperture problem. What is the aperture problem is? Aperture problem says if you assume M to be available, right, and you have B to be available, right? So at every pick, compute something called as capital U. By solving the equation M into U is equal to B. We have M, we have B, we want to find what is capital U, right? Okay, so the nature of M here will be like this. M will be singular, right, if all the gradient vectors point in the same direction. So when they point in the same direction, when it is along an edge, because when it is along an edge, what happens? It doesn't have any other direction, it has to point only along the edge alone, right? So there you actually conclude that you are landing with something called as an aperture problem, right? So this would take you to the next thought process of how this SST, right, can be taken with respect to a texture area. This is your image, this is your SST surface, and this is your texture area which is being presented at the bottom. Now, same SST applied on the edge, right? Its surface area with respect to edge is being presented here. Same SST with respect to a homogeneous area. This is your homogeneous area. You can see here. Take this, look at the edge pixels, see how it is being displaced on the surface level. So this will take you to the understanding saying that you can actually have an velocity estimation at every pixel using one of the iterations of what we have seen using a Lucas canade, right? So how does it do it? So this will take you to something called as an optical flow approach. So what we have discussed right now is there are two types of constraints. One is called as a brightness constraint and second is an aperture problem. To solve this, can we actually use some algorithms? So here we are talking about algorithms for optical flow. So optical flow says that it is an iterative estimation process. That means here we will look at possibly displacement of pixels along x-axis, which is U, and displacement of pixels along y-axis, which is V here. So here we are indicating displacement as D, right? So we will not use U here. Instead, here we are representing displacement as D here. So what is our initial guess here? Our initial guess is there is no displacement at all, right? So there you can assume that there is no displacement, you assume it as 0, right? Now there is a displacement happening. You can say B1 is equal to D0 plus some displacement vector. Why is displacement vector? There's a displacement along the direction. So there's a displacement. D vector means it indicates in terms of U and V, right? Now this is the update that you would like to find. When pixel is moving from one direction to another, every time we are interested in finding the update of the moving pixels. So how do you find the update here? So this takes you to the next thought process saying that if you can approximate it to a function, while you say this is f1 of x minus d1 and this is f2, there I can find the update. This update is nothing but the d vector. You can see here. Once I find the d vector, then I have approximated the moving pixels, right, by saying that my guess is displacement or some value and I am getting the new guess. That's a second displacement. So what's the third displacement? Third displacement d3 will be d2 plus d vector. That means if I have the initial displacement understood, then I can find the displacement of the pixels in the consecutive frame, right? So this will conclude saying that you can actually use an optical flow, right, for understanding the movement of pixels, right? But here, one challenge that will happen is the warping of the image that you want to do is generally is not very easy, right? The reason is whenever you do image warping, I think people know there's a movement of pixels, especially along the edges. So there, it's very hard to approximate and do it in optical flow algorithm, right? So there is another concept called as optical flow aliasing. What is optical flow aliasing? Is here we say that we will try to have a temporal aliasing, which will cause ambiguities in optical flow, right? So the thought process is like if you have moving pixels, we'll have to find the closest pixels that connects to each other, right? So that can be done by using an aliasing approach. Okay, one second. One second. Yeah, sorry, had a battery problem here. Okay, so concept that we have is we have an optical flow aliasing. So the purpose of optical flow aliasing is wherever you have some ambiguities in optical flow, right? Especially this will be more applicable when you have images where the images have many pixels with the same intensity, right? For I can give you some examples. One example is all the water region images. There you can see many pixels with the same intensity. And second is if you have medical image, you can find lot of moving pixels which is captured as part of video which will have the same intensity. There the issue is how to solve such cases is you can actually have an aliasing. So there you can try to look for the nearest match, right? And there you can conclude whether the pixels are similar or not. Okay. So this is about aliasing approach. Yeah. So you can see here, you can see across the frame, there are some moving pixels. We are trying to find the shift of the pixels. So this is the actual shift and this is the estimated shift, right? So when you apply aliasing, right? So even aliasing doesn't give us good solution. So what is suggested in theory is you can go for coarse to fine estimation. What is this coarse to fine estimation is you can build a pyramid of an image and you can build a pyramid of another image in comparison, and there what you can do is you can look at the refinement of the pyramid at every level, right? So there you can try to conclude whether the pixels that you're trying to compare, do they fall in the same region or not. Okay, so this is the first one that I want everybody to understand. So the conclusion here is now you know that there is an algorithm called as optical flow. Using an optical flow algorithm, you will be able to conclude, right, whether there are moving pixels. If there are moving pixels, you will be able to come to a conclusion immediately whether that moving pixels are part of some algorithm dataset. So I can say whether ball is moving or human is moving or any animal is moving, all that I will be able to conclude by using these approaches, right? So taking this as a first step forward, we will now move on to understand the algorithms that are there with respect to optical flow. In optical flow, there are two types of algorithms. The first type of algorithm that is there is called as Horn and Shank. Okay, so the first type of algorithm that you have is Horn and Shank. So I'm not taking through any presentation for it. I will show you directly from the material part so that it is easy for you to understand. So the first type of algorithm that we have is something called as Horn and Shank algorithm. Then the second type of algorithm is something called as Lucas-Kennard algorithm. Right? Second type of algorithm is called as Lucas-Kennard algorithm. Second type of algorithm is called as Lucas-Kennard algorithm. So Lucas-Kennard and Horn and Shank, both of them are used in many type of applications. There are some small
Sir,
differences.
sir,
Yes.
your screen is not visible.
Yeah, I'm sharing the screens. I'm sharing the screen. There are some small differences between Lucas-Kennard and Horn and Shank algorithm. Wherever there are moving pixels, right, and the dissimilarity of the pixels is high, right? So there you can actually decide to go between Horn and Shank or Lucas-Kennard algorithm. Okay. Now I'll share you the screen. Yes. Yeah. Now I'll share you the screen here. One second. Yeah. So are you able to see the screen? Hello. One of you, can you acknowledge? Are you able to see the screen now, please?
Yes, sir.
So the first one is optical flow estimation with Horn and Shank algorithm. This is a very good URL for your reference, right? Which you can take as a use. As I told you, if I have two images, I'm interested in finding the motion part of the pixels. So the moving pixel is basically with respect to the objects. So the motion component will be estimated using the optical flow algorithm. So here we are talking about Horn and Shank algorithm. So what Horn and Shank algorithm will say is, Horn and Shank will say that I will give you an objective function which is E of u comma v, right? So here if you see the inner parameters, right, don't get feared on seeing the equations. There are two images for our reference, image 1, image 2. Okay, and next one that you can see here is this operator. This operator everybody knows, it's a gradient operator, right? Next one that you can find here is lambda. Lambda is nothing but how the weights are provided to regularize it, right? So this Horn and Shank algorithm gives you an objective function which will be applied on consecutive images. What is this consecutive images? If you have a video, I'm going to have two images. I'm going to compare the two images and estimate the value for the objective function. So now the question would be is like, we can have a displacement along the x-axis, along the y-axis. So the objective function will get slightly changed. How it will get changed here? If you see this equation, here we have provided the gradient with respect to u, gradient with respect to v. Now the same thing you rewrite it as gradient of u plus du, gradient of v plus dv. Okay, right? Now the next change that will come up here is we can assume the individual images along the x-axis, along the y-axis, along the z-axis. So along z-axis when you write, it will be I suffix z of p, which will be I2 of p plus w minus I1 of p here. Okay. Same if you can write it for I suffix x of p, it will be displacement along the x-axis, rate of change along the x-axis. I suffix y of p will be rate of change along your y-axis, right? Now if you go back to a Taylor series that we just now discussed, the equation will change as I2 of p plus w plus dw, right, minus I1 of p. If you take it here, right side, what you will get is all these components, I suffix z, I suffix x, and I suffix y. Okay. Now, when you further expand, the question is like we are interested in finding the rate of change. What is the rate of change? We are interested in finding du and dv, right? So if you take from here, we can rewrite the equations as saying rate of change with respect to u, rate of change with respect to v, right? Now if you see this individual equation parameters, this will be provided from the earlier one here, right? So we will have finally an equation which will be written like this. This equation will have components with respect to x, component with respect to y, rate of change with respect to u, and rate of change with respect to y, right? That is v here. So this is the general algorithm which we will write here. Now our question is, given an image like this, we are interested in seeing the motion part of the image in the consecutive frames. So this is with respect to Hall and Shank algorithm. Now the same thing if you take it to next one. Next algorithm we would suggest is a Lucas-Kennard algorithm. This is a very good URL for learning Lucas-Kennard. So I am sharing you this link. Right. So as far as Lucas-Kennard is concerned, here we again assume that we will be able to have objects being tracked from frame to frame, and Lucas-Kennard will say that it will be able to minimize the sum squared error of brightness constancy equations. What is brightness constancy? We have already discussed, right? Just now we have discussed about this. And when you go to the Lucas-Kennard approach, this will be concentrating on finding the eigen given image. As you all know, eigenvalues corresponds to the features of the given image. And as you expand and see, this is how Horn and Shank assumes, right? What does Horn and Shank assuming? It's assuming a brightness constancy. It's applying a Taylor series, right? And gives you an equation for you. What does Lucas-Kennard does is, Lucas-Kennard again takes the same concept, but only thing is here, it will represent everything in terms of an eigenvector. And it will give you an equation like this. Okay. Now, this is the theoretical aspect of looking at optical flow. Now, the next question people might start asking is why this is being discussed and what is the purpose of it. See, today, when you talk about deep learning architectures, especially if you take deep learning CNN, right, there is a lot of architectures that has combined deep learning with optical flow. I think you can see here. Estimation using deep learning, right? Then light-weighted optical flow CNN. Like this, many works have come. So I thought in this agenda of discussion, let's look at how this can be taken together with respect to a security domain. So in terms of security domain, the context is activity recognition. Okay, in this the context is activity recognition. So here we are looking at activity recognition with respect to humans, right? So why do you need an activity recognition? This you can find it very nicely from this blog. Why human activity recognition is important. This is available under machine learning mastery.com. So what do we talk about activity recognition is, we are interested in finding out whether a person activity is suspicious or not. So why is a suspicious activity important? It is important to understand that the person's actions are not normal, right? So we are interested in finding the suspicious activity of the person. So let's look at a possible implementation for a deep learning with an optical flow implementation. There is a URL that is shared to the participants. I think people would have got this URL. I think, can you acknowledge please in the chat box? If you can check your mails, you would have got a Google Colab link which I have shared. Participants, can you acknowledge please in the chat box? Yes, no, something, please.
Yes, sir.
Yeah, fine.
Yes, sir. We got it.
Fine. So this is the URL. So this URL of Google Colab link will have the steps for putting everything to step by step, right? So this URL code is what I have shared to the members morning, especially from a GitHub link. Once again, I'm taking that GitHub link also for your reference. I think that also participants would have gotten the mail, because you should know the source from which we are giving the data. Those are 6. Yeah. Yesterday's face detection code also I have shared to the members. So, plus I have shared this also. One second. I'm now, yeah, I've now shared the desktop. Yes. Okay. So what I'm showing before you on is from this URL, that is fault detection with CNNs and optical flow. Right? Fault detection with CNN and optical flow is the URL page that I have taken. This is a working code. Small modifications have been done for all your reference. Now, if you go to the URL of the GitHub, right, they would have the steps for pre-processing, as you can see, and they would have given you the Python code that is being used, right? And as you come down to the page, no, they would actually give you the repository details and how to start working with the dataset, right? Okay. So the thought process is, if we have a data of a video which is extracted as a set of images, can we actually understand the actions in the given dataset? So there are possible good datasets which are there in the internet. So the dataset is put up for you. UR fault dataset is one dataset that is used by the people here. This is UR fault detection dataset. Okay, as you can see here, this is from University of Wisdom. So here, as a person walks, right, then as a person falls, right, it's taken as an activity and it is being detected. So the data sets are there. So this is one of the data set that is taken as reference for all your information. So here, as a next step, what has been done for all of you to work is, whatever is there in the GitHub is being taken step by step and it is provided in your Python notebook file, right? So here, if you can see here, the first step you are supposed to do would be like, you are supposed to access the data link. Okay, so you go and click, you'll be able to access the data link. So that is your data link provided, as you can see here, right? So that is a data link provided. So this is your data link folder. The next is, you need to create a My Drive, because since if you are working on Google Colab, you need to create a drive to mount all the files. So that is the next step, right? So then you can run the code directly from the link as we have provided here for your reference. This is your GitHub code link. So you can go here and you can run it. Okay, you can run your GitHub code link from here, right? Then next step is, you need to mount the data where it is being stored. So you would have created a drive. You can mount the drive by running this code part. Now I'm running everything on the GitHub code. Please see, all of you. You can also do participants, because this link is shared for your reference. Okay. Then Next step is you're mounting the drive, right, where the data has to be extracted, right? Then you can connect with your ID. Then rest of the code, as you can walk down, this all is the code that is provided from the deep learning perspective, right? Now, if you look at this here, as I told you in the beginning of session, we are trying to see a code which is based on Keras and TensorFlow, right? So here, as you can see here, the type of model is sequential model. Other layers, they are trying to use convolution, max pooling, flatten, and next is the act function. They are trying to use an activation function. So there's an activation layer, and there is a dense operation, there's a dropout operation. The purpose of dropout is wherever you feel that you do not want to use all the weights in the model, there you can go for a dropout. And next important thing is about optimizers. Here the type of optimizer that is being used is an Adam optimizer. Okay. And next is about a normalization. They are using a batch normalization, right? This is not required for us because they are trying to have model checking points at any once a model is getting created, right? Then next what they are doing is they want to use performance metrics. So here they want to use confusion matrix and accuracy score, right? And they are also using an advanced activation function which is called as ELU, that is exponential linear unit, right? Then rest is all they are trying to connect to the data folder. Then the weights they are trying to have here. Here the type of architecture that is used is VGG architecture. The type of architecture they have used is a VGG architecture. Then next what we should understand is about all this. We said already that every architecture has got some hyperparameters. So the hyperparameters includes learning rate, batch size, weight value, number of epochs. So what is hyperparameters? Whichever is defined by the developer is called as hyperparameters. Whatever is estimated by the model is all parameters. So what is all estimated by the model? As you can see here, you will find confusion matrix and accuracy score, right? Then then they have a training folder file. So here they are estimating the accuracy here. Okay, then here they are looking at two types of classes here. One class saying as fall and another class saying it is not a fall. So you are summarizing whether it is a fall or a not a fall in the activity here. Then this is simple. I think people can understand. They're taking all the videos which are there in the folder, right? And they are classifying it as fall or not a fall. Then let's not go line by line. Yes, this is about the VGG architecture. Why I'm walking through certain piece of code is in case you want to expand your this code for your research or for your project, this is how you should look at it. So here they have thought of an VGG architecture. So this is for one stack of VGG. This is another stack of VGG, right? As we discussed in the CNN, no? Convolution, pooling, fully connected. Here in VGG, what they say is they have convolution and they have a pooling, right? So this is one stack. This is stack 2. So like this, they have used multiple stacks of VGG. So what you can actually do as part of your research or for your learning is, now they have done like this. No? You can take one from here. Okay, I'm just copying, showing a small way of how you can modify and learn the code. You can copy this, you can paste. So what happens? There is one more stack of VGG which is being created as part of the model. So the thought process is the more the number of stacks, the better is the amount of learning, right? So here you can always go inside and you can change certain other hyperparameters, like you can change the activation function. Okay, and you can check how the model works. Then what they are doing is they are doing a flatten operation. They are calling a dense function here. Then is a weight initialization part. So for weight initialization, this is a code for the weight initialization procedure. And as you all know, the output of any deep learning model will create a file, which is a weight matrix file. Okay, so it'll create a weight matrix file. And as I told you in the beginning of the session itself, when you want to use the model again, you need not run the code if the model hyperparameters are same. All you need to do is you need to take the weights file. Okay, so all the weights values of the given data after learning will be available in the weight file here. So this is the code they have written for feature extraction, right? And this is the code they have written for the training process, right? Then this is what we should actually understand from the code perspective, right? And we have said they have handled model checkpoints. So this is a code for model checkpoints. Okay. That's it. So this is the code procedure. So you can take this and use it for your reference in case you want to extend your research, especially with respect to fault detection, right? Now, keeping this as a first step of information, let's go on to the next part. One second. If there are any questions, please participants can post the questions. I've shared you the URL. I've also shared you the possibility of running your code with a clear explanation in the Google Colab. Any clarifications, you can post questions in the chat box. Participants, any clarification? Any clarification, please?
So, like if we increase these rights, what will be the change over the codes?
Yeah, stride as such, as I told you, ma'am, you can actually have stride as 1 or 2 or 3. If you are going from smaller images to high dimension images like aerial images, you can have a highest value for the stride. The stride can actually have a maximum of half of the width of the image. If you say the number of pixels along the column is going to be 30, you can have stride till 15. That's what research papers speak.
Okay, thank you, sir.
Yeah, thank you. Thank you. Any other questions? Any other questions from the participant side? Any questions? Any questions from participant side, please? Okay.
Sir, we need a how to know confusion matrix.
Not getting what you're saying, sir.
Sir, I need explanation of confusion matrix.
Confusion matrix, sir. Okay, fine, sir, fine. Okay, I've taken that question, sir. Anyway, I will spend some time the last 10 minutes on performance metrics. That time, surely I'll spend time on confusion matrix, sir. Any other questions? Any other questions from the...
Sir, how to find the intensity value, sir? Pixel intensity value.
Well, pixel intensity, you have functions, no, ma'am. You can actually, pixel intensity corresponds to the grayscale levels, right? So you can use the function to find the pixel intensity value. Which type of data set you are working with?
Sir, I told underwater image, sir.
Yeah, it is only going to be color images only, no?
Yes, sir.
Directly find pixel intensity estimation. You have functions for pixel intensity estimation.
Sir, when we are doing the haze removal, that
Yes.
time that scattering, back scattering and forward scattering is there, no, sir?
Yes.
So to improve the image intensity, we want to correct it, no, sir, for that, sir.
Yeah, you want to, what you want to do, ma'am? You want to do intensity improvement. Then in that case, you can use filters.
Okay, sir.
Filters will actually improve the intensity values, no, on the given image.
Okay.
So you can go for intensity correlation algorithms.
Okay.
That is one way, ma'am.
Okay. Thank you, sir.
Thank you, ma'am. Thank you. Okay. Fine. So any other questions from participant side? Okay. See, the first part is of the session. I want everybody to know about optical flow. Very interesting topic. And wherever you are looking at motion component, you can immediately say that use optical flow algorithm, right? So that's the strength of optical flow algorithm. Now let us go to the next part of discussion. So next part of discussion, I want to say an algorithm which is there, right, which people will not forget also, right? There is an algorithm called as snake algorithm. Okay, right? It's an algorithm called as snake algorithm. See, the snake algorithm is also for motion estimation. What is the purpose of snake algorithm is, we know that if you take a snake and you put it within a small box, it will actually contract itself and fit it to a box. And if you take the snake and put it to a bigger box, it will expand and it can fix to the box. So there is an energy component which is assumed to be an internal energy and an external energy for the pixels. I think people should understand. If I assume a boundary for the pixel body for the snake, there is an internal energy, there is an external energy for it. So based on it, there's an algorithm there which is called as snake algorithm. So people want, you can actually have a look at snake algorithm also, right? So this is next one which I want everybody to know. The next in discussion which I'm planning to take through is about transfer learning. A lot of people talk about transfer learning nowadays. Even our discussion, we are talking about transfer learning. Why transfer learning to the problem? See, as far as transfer learning is concerned, the discussion behind transfer learning is we want to take the knowledge that we have learned from some other domain and we want to provide it to our domain. So that is where you can go for transfer learning, right? So there is a source domain, there is a target domain. Our knowledge that you have learned from the source domain, we want to bring it to the target domain here, right? So the usual process in learning systems are like what you see in the slide, right? You have multiple datas. From every data, you have a learning system and you develop and improve your learning, right? Now, your concept of transfer learning says, if I have multiple databases which corresponds to different domains, can I learn something from that and take it to something called as knowledge, right? So when I'm getting a new database, can I automatically learn? That's the next thought process here. So this is called as transfer learning. So you're bringing your learnings from one set of data to a new set of data in the target domain, right? So how do you connect it, right, for understanding? Suppose you look at a flower. The flower is pink in color. Okay. Now you have learned flowers. So you know there is a flower which is pink in color. You see some other object. That object is also pink in color. And that object also has a shape which is closest to what you have learnt in a flower. Please try to understand. Okay. So that case, you are trying to come to some sort of understanding. Okay, what I'm seeing is not a flower, but I understand that it has got a shape, it's got a color similar to what I have seen from the flower. So this is the strength of transfer learning. So if a model is built using transfer learning, it can actually learn things over the time without you training again and again, right? That means if you are giving a new set of data also, the model will be able to recognize because it has learned already from many data, right? That means it has learned about many classes of data. So that's a concept about transfer learning. So transfer learning will say that if you have a data set which is not labeled, that data set can be learned using a transfer learning model, right? And next, people suggest that if you're going for a transfer learning, then it is something similar to a multitask learning. What is multitask learning? If you look at stars, galaxies, right? If I want to learn about stars and galaxies together, right? You connect something from here and learn about stars. You connect something from here, learn about galaxies. Finally, you have learned about stars and galaxies, right? So the source domain from which you are trying to learn will give you some sort of distribution. You can try to take the same set of distribution and adjust it to the target domain, right? Okay. So this will take you to the next thought process saying, how will you learn about the parameters? So there people suggest that you can go for a support vector machine because a support vector machine will be able to find the coefficients of the source domain, right? And with the target domain that you have provided, you can again find the coefficients using support vector machine, right? By initializing the search with what you have learned from the source domain, right? So find coefficients W suffix R using SVMs, initializing the search with W suffix S. Okay. Now this will get you to a thought process saying that I have found common features of all. These are all my images, right? So I learned about every image set of features. So what is my model having? My model has learned about different type of features, right, from different type of images. So this is something called as feature transfer. Please understand the concept. So the model has learned many features. So now the model is able to connect different features from different images. This is called as feature transfer. Now the question would be is like, what is domain adaptation? People are saying that you are taking from one data set a domain and you are trying to adapt it to the next domain. What is a domain adaptation? It is like this here. If you look at this, you see that there is a source class, right? The source class is indicated as plus, and the other source class is indicated as minus here. And there's a target class which we are giving it a circle. Now, this is your target class. Now, I'm interested in saying that if I have a transfer learning model, I have learned something from here, I have learned something from here, right? With this two learnings, I'll be able to learn this target class, right? So my target class is learned. Okay. Now, in overall, if you're going to go for a transfer learning model, the summary is like this. You need to have a source domain data, and you can label the source data, and you can try to have a learning. Now, when you give a target domain means what? Some other new type of data which the model has not learned. There, it needs to understand that it is not having any labels. Now, it has to compare its learning from the target domain together with what you have learned from the source domain, run through a domain adaptation algorithm, and then say that I am able to predict the respective class. Like I told you, I have learned, or the model has learned about different flowers. You are giving a huge set of data which are just images. Somewhere it's able to relate and see that this is something similar to a flower X of a same shape, of a same color, right? It gives a class name for it. So this is what is called as domain adaptation problem. And what generally being said is like you can apply a covariant shift, right, to make sure that the classes of data that you're learning, right, this is the classes of data, right, which is marked with circular. It's what you want to learn. Either they will fall into this class or they will fall into this class. Now, people will get a next question saying that, okay, what are the transfer learning architectures? Okay. So, in transfer learning, there are many architectures being available. Most of the architectures are dependent on existing architectures that are there. Okay, let's look at the transfer learning architectures that are there with respect to common usage, right? So here we look at 4 transfer learning models which are available, right? The first transfer learning model is called as inception, exception, VGG, and next is ResNet. Inception, VGG, exception, and next is ResNet. As I told you, what is transfer learning? You are trying to take the learnings from one set of data, right? And you are trying to provide it to the another set of data because there is a source label and you want to adapt it to the target label. Source label, you want to adapt it to the target label, right? And there is also one more information about transfer learning. People will say that wherever you are not able to create large size of data, right? I have only 100 images. I cannot create 1000 images. So there you can go for transfer learning. The best example is somebody is trying to develop a system to talk about detection of fire. You cannot create big fires, right? You can create only small fire, but you will say that tomorrow it can detect a big fire also. In such cases, you can go for transfer learning. So transfer learning is also used for places where you cannot create large size of data, right? Now the next question somebody will ask is like, where should I not be using transfer learning, right? Okay. See, if you are giving data for training process in a transfer learning model, but the data set is almost very similar, it doesn't have big changes, right? We compare one class with the other class of data set in the training, it is not varying much. There in such cases, what happens is transfer learning will not work, right? So transfer learning always looks for some data set which is having some sort of difference among themselves in the representation. So in the architectures, as I told you, the first architecture that's very popular is your inception architecture, right? As you look from here, inception architecture will actually talk about layers where it will have convolution layers, but you'll have varying convolutions. So at the first stack, you will have 3x3 convolutions. Second, 5x5 convolutions. Third, you will have 1x1 convolutions, right? This is an architecture that was proposed in 2014, right? And as you all know, we are now in 2022, right? So this architecture model also will show you one more thing called as 1x1 convolutions, right? Okay. So this 1x1 convolutions as such indicates the filters. So all this 1x1 convolutions will have 128 filters for dimensions and for reductions, right? And it uses a rectified linear activations. And what you see at the top here, that is 3x3, 5x5, 1x1, all of them are basically for feature extractors. So you want to extract features, so you have 3x3, 5x5, you have 1x1, right? Then next, as far as performance is concerned, it is almost similar to CNN because here also you see convolution layers coming up, max pooling layers coming up, but the performance is said to be better compared to CNN, right? Okay. And this architecture, which is inception, was originally called as Google Net, right? That's about your this architecture. That is inception. The next one is called as exception architecture. This exception architecture is actually the architecture that was proposed by the owner of Keras, right? Who actually maintains the Keras framework called as Francois Charlotte. So he is a person who has proposed this architecture called as exception architecture. What is this exception architecture? It says I can give you stack of code like this, right? And this stack of code can actually have three types of flows. One calling itself as entry, and next is called as middle, and third is called as exit. Entry, middle, and third is called as exit. Here also you can see convolution layers, ReLU activation function, max pooling functions. You can see convolution layer with varying strides, right? So this is about this architecture here, which is nothing but your exception architecture. This architecture is part of Keras framework. Third architecture is called as VGG architecture, right? So what is this VGG architecture? This VGG architecture stands for something called as Visual Geometry Group Architecture. And this is an architecture which was proposed by University of Oxford, right? So this VGG architecture says that if you have varying training models and the images are going to have varying features, if the images have varying features, there you can go for a VGG architecture model. These are variants of VGG architecture that you can see here, right? These are all variants of VGG architecture that you can use. So this is also very popular. Then next is ResNet architecture, right? So ResNet architecture as such is again a very standard architecture which resembles to what you see in your CNN. But here this ResNet architecture will use a stochastic gradient, right? That's the only difference here. But rest of the things will look as the same. You will have convolution, you will have pooling, as similar to what you see in your CNN, right? And ResNet as such will introduce concept of blocks. ResNet architecture will introduce concept of blocks. You can see blocks numbers being put up in ResNet architecture, right? And disadvantages, this is architecture is generally said as complex. It's very hard to handle. And this is the comparison of different architectures that we have discussed in transfer learning. The first one is inception architecture. You can see complexity is low, speed is high. Inception, speed is high. VGG, the speed is low. ResNet, the speed is high, right? And with respect to accuracy, what is said is like this. Inception has a highest accuracy of 0.790 and 0.945, right? So these are the architectures, and all these architectures have also got code implementation. For example, if you say GitHub ResNet architecture, if you say GitHub ResNet architecture, you will find code for GitHub ResNet architecture being available, right? So you can take the same source code as I'm showing you here, and you can also use it for all your projects, right? So now what we have seen is about the different transfer learning architectures. So in summary, the transfer learning can be used in two places. One, where you have a data set, you want to learn something from the data set and adapt it to a new data set, which is going to be used in the model. There you can actually go for transfer learning. Second, if you have a data set which cannot increase in size at all, right? I have got 100 images. You cannot go more than 100 images. In such cases, there you can say that I will go for transfer learning, because transfer learning will automatically be able to create varying features from the given image, and from that it will be able to say that given any data set similar to the image, we will be able to conclude that the data set is having features similar to the original data set. So a best example what I would suggest to the people is You can
Sir,
actually.
excuse me, sir.
Yes,
The
ma'am.
screen is not visible, sir.
Okay, fine. Yes, ma'am. Yeah, I'm getting it. So in such cases, you can assume that your model creation is perfect and you can use the same model. Now let's come to the next part. One second, next part. So the next part of the session, what we will go with is understanding the metrics, because there's been a question from the participants about the metrics part. One second. Meanwhile, any other questions from participants? Now we have seen three things. We have started with activity recognition. We have shared you a code for your reference. Second, we have talked to you about transfer learning. So now we have seen about transfer learning architectures. We are given a summary about the difference between deep learning and transfer learning. Any other questions from the participants? There was one question related to medical data set. I asked the member to write me a mail. I have not received the mail. Please clarify me if you have written the mail and it happens to stay in my junk folder.
Sir, while teaching transfer learning, and he showed me as like the teacher extracted images of different input image, no, sir?
Correct, ma'am.
Sir, is that meant for the training phase or the implementation phase, sir? The class segregation?
It's meant for the training phase, ma'am. Because see, whatever model learning process we create, we are going to use only the model. So, for example, if I have created a transfer learning model using ResNet, right, to learn about, to train about different flowers. Okay. Now what I give you is only the model file. Correct, ma'am? Suppose I am giving you an images which are related to fire. It will try to connect and say that this is having a accuracy score of 0.5, similar to a rose image where there is little bit of red or pink color pixels.
So like somebody used the annotation and the mask, sir, in place of features. So how does it work well for this model, sir?
Yeah, see, annotation as such, okay, annotation and mask, because we know we have got mask CNN. Okay, thanks for asking the question. See, a mask is actually about bringing one more learning about the feature of the given image. That's all, right? And annotation as such is more about how we are trying to give an annotation to the given image. For example, there's a cup, there's a flower, right? You annotate the images. So when you do annotation, the advantage would be is if you give a scene, you will be able to annotate the scene with the different objects in the scene. Suppose I give you annotations with respect to cup, table, chair. If tomorrow if you give an image where there's a chair and a cup, it will automatically annotate and say that there is a table and a chair. Madam?
Yes, sir. So like how does these parameters will work for the transfer learning model, sir? That is like I could not correlate. If I'm talking about the feature, like feature is good enough to segregate classes. Like if I'm trying to annotate or if I'm trying to generate mask and then train my network. So like how this transfer learning will work for that certain images, sir?
Okay, you are asking about how transfer learning will work. In case I
For
go,
this mask, yes, sir.
yeah, see that case, ma'am, we have got architectures which actually are now available with respect to transfer learning with mask based itself. So you can use such architectures.
Okay, thank you, sir.
It is there actually. We have got architectures which speaks about transfer together with mask CNN. So it is available. You can use that.
Okay, thank you.
Okay. 1 minute, 1 second. I'll also check. Yeah, there is. You can see here, no, transfer learning with mask CNN. Ma'am, can you see the screen?
Yes, sir.
Yeah. So you can use such architectures. See, actually, from state of art of research, what I would generally suggest to the people is a deep learning architecture, a transfer learning architecture is a black box, right? You give modification means one way of modifying is you can actually vary the hyperparameters. Like I told you, number of epochs is 10, you train with 100, or you vary the number of convolution layers, you vary the activation functions, or you introduce new stack of layer. That is one modification that you can do. Other modification that you can do is you can try to approximate by specifying the regularization that you want to provide. What type of regularization you are providing is very important. L1, L2, what type of regularization. Other state of art research is, rather than you fixing the hyperparameters, can the model tune the hyperparameters by itself, right? And that is other thing which you can actually look for. So when you do all this, your architecture is varying. There is some novelty in your deep learning architecture. In fact, now there is a lot of research. In fact, one of my scholars also completed writing a paper on hyperparameter tuning, right? Rather than you fixing the hyperparameters, no, can you vary the hyperparameters for an architecture? You can do it in CNN also, right? You can vary the hyperparameters for CNN. Now, when you decide that you want to have a mask based object recognition or feature extraction like that, you can directly go to the CNN which is there, because we have got mask CNN is there. Use the mask CNN, and there you can vary the hyperparameters and you can check the model.
Thank you, sir.
Okay, this is my limited understanding. So I think it might help the participants also. Okay.
Sir, one question. Sir, mask is basically for the segmentation. So
What's it?
it's more
See, actually, when
the segment, the image is segmented, and the segmented images has been used for the training, right?
okay, so your question is what, sir? Your question is asked. Your first question.
I just you were explaining about the transfer learning along with that mask-R. So I just wanted to know, mask-R, to my knowledge, mask-R is mainly concentrated on the segmented image.
Correct. Mask CNN is especially for segmentation, right? Madam's question was like, I also want to think about transfer learning there. So my suggestion was like, there are now architecture examples where you can provide transfer learning with mask CNN itself.
Okay. Sir, basic question is like, so we already have a pre-trained models actually. So, which means the model is already computed, so we can use those models for our data sets. Actually.
Correct, sir.
This transfer learning differs from the pre-trained models.
Okay, fine. See, how does the transfer learning differs from the pre-trained model? Okay, very good question. See, transfer learning architecture is also a deep learning architecture. First, that we should accept. When you look at a transfer learning architecture like Inception or ResNet, it also resembles there is a convolution, there is a pooling like that, right? But internally, it gives you some special layers like block layers, for example, through which it says that I can learn something different from the given data, right? So you give varying classes of data also it can learn, right? And when it wants to take the learning, right, it can actually do a domain adaptation on the test data that you're giving, right? So if you give a test data which is not similar to the class of data that with which you have trained, but still it can compare and say that this falls into class X of a varying score of 0.2, 0.3 or 0.1 like that. That's how the transfer learning works.
Here we will be using two different data sets. Say for example, one data set, for example, I have a birds data set and then I have a human. So both are different, extremely different data sets actually. But how does, but pre-trained model doesn't consider that much. So the model is there, so whatever be the data set I am giving, so it will actually try to classify.
Here also like that. Here also it will do the same. But the speciality is in the type of layers that it provides. That's what I told. A transfer learning architecture also resembles a deep learning architecture.
Okay. No, most of the time when we use a pre-trained model, so the pre-trained model's accuracy is improved only when we have this have this parameter enabled, the transfer mode. So we have an option actually. So we have to set that option, transfer learning equal to true something.
Yes.
It actually improves the accuracy. So I just wanted to know what is the connection between, or what is the why do we need to, most of the time when we use a pre-trained model, so we have to enable this transfer learning parameter. So why do we have to do that, and what is the connect? That's what I want.
So somebody is muted. Okay. See, suppose I've got 100 images and I'm trying to have 30 images as positive, 70 as negative. So my model is perfect because it has got more amount of negative images, right? And the false positive rate is going to be very low. And next question somebody might ask is, okay, that model is fine, but what will happen if there are some challenges with varying brightness, noise like that? Again, I go and increase the number of positive samples, increase the number of negative samples, provide intra-class data there, saying one with a varying brightness, one with high brightness like that. My model is perfect. Do you agree with me, sir? Hello, sir?
Yes, sir, I agree, sir.
Yeah. Now, when you go from there and you actually come to architecture like GAN, okay, GAN, Generative Adversarial Network. Okay, what GAN does is like GAN says that whatever type of data that you provide is not enough. All right, I will create some data for myself. Right. For example, if I give rotation of my face for 90 degrees, my GAN will say that I will rotate your face 180 degrees also, and I'll recreate one. Because tomorrow, if your face is rotated at 180 degrees, I will still recognize it as Senthil Kumar. Okay, that's how GAN works. It works on the concept of probability distributions. So, am I clear?
So, GAN is gated area network.
Yeah, generative adversarial network. Generative adversarial network.
But that is the same concept we used in CNN also, sir. We actually give a probability distribution based on the distribution.
CNN doesn't have any sort of probability distribution concept. CNN, in fact, doesn't have any remembering capability itself. In fact, that is where when you go from CNN to RNN will have remembering capabilities. It can compare the past data and learn the data. When you come to GAN, it can generate data by itself based on the probability distributions, because there's a generator, there's an adversary. Okay. Now, when you come from there to transfer learning model, transfer learning architectures are again similar to the CNN architectures, but only thing is the architectures gives special characteristics. Like it says that I will give you a transfer learning capability using a block layer, right? I give you some sort of transfer learning capabilities using my stack level learning, because we say that one set of layers are exclusively there for learning the features alone, right? So there, if you give multiple classes of data, the feature extraction layers that are there in transfer learning will learn the features very nicely. So when you give a new class of data also, it can relate to the classes with which it has learned, and it can say that, okay, this resembles to class 1 or class 2 with so-and-so accuracy. So the feature extraction layers, which is part of your transfer learning, gives you the capability to shift or learn from one domain to another domain. So, have I clarified you?
Yes, sir. Yes, sir. But still, I have a question. So, like, we have two different domains actually. But that is my.
Yeah, though there are two different domains, please understand, sir. One domain is related to another domain in terms of features. Am I right? For example, if I ask you to look at sky, sky is blue. I show you a chart paper, it is also blue.
Okay.
Huh?
Yes.
If I show you a sky where there's a circle there, the cloud is circular. Here I show you a chart where the kid has drawn a cloud with circular, semicircular. Your thought process what it is also like cloud, but it is semicircular.
Yes,
Right?
sir. But okay, sir. I'll come to this example itself. So, like for example, I have a chart paper, so which is very similar to the color of the sky.
Correct.
I have a cloud. Okay, so I drawn a cloud actually. So when I try to give it to the model to classify it, so it should not classify it as actual cloud. Instead, it should be classified as different, right? So it's two different things. One is an actual and other is a.
It will not classify as cloud, but it will be able to classify and say that it is 50% class score similar to cloud.
Okay.
Okay. So you as a developer, you are looking at class scores of above 70%. Then in that case, this will not fall into the class at all.
Okay.
Is it clear?
Yeah, correct.
We are the model developers, sir. Right? Okay. So how much knowledge we imbibe to the model is strong.
Yeah.
Okay. I just take a quick thought process. People were asking about the performance parameters. See, there are many performance parameters. One performance parameter is precision. The next is accuracy. Then you have recall. Then you have F1 score, right? Then you have confusion matrix. This metrics, I need not say you the formulas. If you go to internet, type precision, accuracy, you'll get good URLs towards data science. Now, the question that was asked by one of the participants is, what is the importance of confusion matrix? So confusion matrix actually gives you the variation between positive and negative samples. By looking at a confusion matrix, you can actually come to a conclusion. How many positive samples have been classified as positive samples? How many negative samples have been classified as negative samples? Right? That's the advantage of your confusion matrix. And in fact, confusion matrix will also give you insight with respect to the classes. If there are 5 classes, each classes has got positive and negative samples. So from a confusion matrix, I can actually conclude how much amount of my classes have been predicted correctly. So all research papers expects a confusion matrix to be represented. This is first information for everybody. Second thing, okay, what about the F1 score? Where should I go for an F1 score? Right? Wherever you feel that there is a possibility for outliers to occur in your data, you want to understand about the outliers, there you can actually go for a F1 score. Okay. Madam, hope I have clarified to you about confusion matrix. Okay, one participant asked this, so I clarified. So that's it from my side, and if there's any other questions, please post it, or you can send it as a mail. So as the experts from the organizers have clarified to you, I work on the similar line. I completely work on video analytics. So my bread and butter on my research area is completely around machine learning, deep learning, and video analytics. Now I'm little bit involved into transfer learning also. So my data that I work is completely around image and video data. Anything in these lines, you have some clarifications, please always write me a mail. Thank you so much, and thanks to the members, Dr. Solomon ma'am of Madras University. Thanks to the other faculty members. Thanks to Lavanya ma'am, and thanks to other organizers of this workshop. And I convey my sincere thanks to my PhD guide, Dr. S.N. Shivanandam sir, former professor of PhD Tech. He's a person to whom I should give my credit, because all my learnings, whatever I talk, is actually with sir's experience. That's all. Thank you so much. Thanks to all the members. Madam, thank you, ma'am. I conclude.
Thank you. Yeah, thank you, sir. Few more minutes for a formal vote of thanks, sir, please.
Yes, ma'am. Yes, yes.
Sir, thank you very much. Big thank you to you, sir, for your wonderful session, informative, useful session for our participants. I am Dr. Chitra speaking, one
Yeah,
of the
thank
organizers.
yeah, thank you, Chitra
We
ma'am.
are very happy to hear you for all the past 3 days. It is highly useful for their research, sir. Thank you so much.
Thank you, ma'am. Thank you. Pleasure, ma'am. Thank you.
Yes, sir. So we'll have a formal vote of thanks, sir, please.
Yes, ma'am. Yes.
Mhm.
Respected and our most distinguished speaker of the day, Dr. T. Senthil Kumar, Associate Professor, Department of Computer Science and Engineering, Amrita School of Engineering, Honorable Professors, University authorities and research scholars, on behalf of Department of Computer Science, University of Madras, I deem it a great honor to propose vote of thanks for the session on Secure Network Analytics with Deep Learning and Transfer Learning. I would like to thank our distinguished speaker, Dr. T. Senthil Kumar, for making excellent presentations and making this seminar interesting and meaningful. We are really enlightened with your knowledge and presence, sir. The hands-on that you gave will definitely help the research scholars to kickstart the research on image processing, activity recognition, etc. A special thanks to the organizing committee and the university authorities for their unflinching support and coordination. Our heartfelt thanks to all the participants for active participation. With these warm words and a kind message, we move to the end of today's session. Tomorrow, the session is on dental image processing using deep neural network by Dr. P. Shanmugavadivu, Professor and Head, Computer Science and Application, Gandhigram Rural University. Thank you.
Sirs, thank you very much for your valuable time and magnanimous knowledge transfer, sir. Thank you so much.
Thank you, ma'am. Thank you. Stay
Yeah,
safe
thank you.
and best wishes to all of you. Thank you all.
Thank you, sir. Thank you, sir. And dear participants, kindly fill in the feedback form. And for tomorrow's session, there's a slight change. We are going to have Mr. Siva Tirumalizai, founder and CEO Nasotech USA, going to address us on new technologies in cloud for AI. Okay, so don't miss the session tomorrow. Tomorrow you're going to have a really a mind brainstorming session on